Hello everyone. Today we are going to analyze this beam using moment distribution method. Before analyzing, let us see the beam one time. In this beam, there are three spans: span AB, span BC, and span CD. Also, there is a overhanging span DE. In the span AB, there is a point load 40 kN acting in the center. In the span BC, there is a concentrated moment 80 kN meter. It is acting in the clockwise direction. In the span CD, there is uniformly distributed load 48 kN per meter acting for the full span. In the overhanging span DE, there is a point load 40 kN acting in the point E. The moment of inertia for the span AB is 3I. The moment of inertia for the span BC is 2I. For the span CD, it is 2I, and for the overhanging part, it is I. AB and BC are 4 meter long. CD is 5 meter long. The overhanging part is 3 meter long. In this beam, there are 7 moments we have to find. In the point A, there is a fixed support. In the fixed support, there will be a moment. Here, the moment is MAB. In the joints, there will be 2 moments. In the joint B, there are 2 moments, MBA and MBC. In the joint C, there are 2 moments, MCB and MCD. And in the joint D also, there are 2 moments, MDC and MDE. So totally we have to find 7 moments. Also, we have to find 4 vertical reactions, RA, RB, RC and RD. In the joint D, we can easily find the final moments because on the right of D, there is overhanging. To calculate MDE, we have to multiply the point load 40 kN with the overhanging distance 3. When we do that, we are getting 120. MDE is acting in the anti-clockwise direction, so it should be negative. In this case, we have to apply a negative sign with the load so that we will get a negative moment. The values of MDC and MDE will be same, but they will have the different signs. MDE is acting in the anti-clockwise direction. It should be negative. MDC is acting in the clockwise direction, so it should be positive, but both of them will be having the same value. In this concept, we can calculate MDC very easily. For that, we have to just change the sign of MDE. When we do that, we are getting positive 120. Now, let us calculate the fixed end moments. First, let us find them in the span AB. In the span AB, there is a point load 40 kN acting in the center. The formulas for the fixed end moments are minus WL upon 8 and positive WL upon 8. Using the formulas, we are getting M of AB and M of BA. Now let us take the span BC and find out the fixed end moments. In the span BC, there is a concentrated moment 80 kN meter acting in the clockwise direction. This moment is acting in the center. The formulas for the fixed end moments are positive m upon 4 and positive m upon 4. Using the formulas, we are getting m of BC and m of CB. Now let us make the fixed end moments in the span CD. In the span CD, there is UDL 48 kN per meter and it is acting for the full span. The formulas for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. Using the formulas, we are getting M of CD and M of DC. We have calculated the fixed end moments in the spans AB, BC and CD. No need to make the fixed end moments in the overhanging span. In the moment distribution method, we have to find the distribution factor. We have to find the distribution factor only in the joints. Here there are three joints, joint B, joint C and joint D. In the joint D, we don't have to find the distribution factor because on the right of D there is overhanging. In this case, we can easily say the distribution factor. The distribution factor for the overhanging side will be 0 and on the other side it will be 1. So the distribution factor for DE is 0 and for DC it is 1. In this case, we have to find the distribution factor only in the joint B and the joint C. To find out the distribution factor, we have to calculate the stiffness. Let us see the formulas to find out the stiffness. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with a roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. Now let us calculate the stiffness values. First, let us calculate in the joint B. From the joint B, we have to calculate two stiffness values for BA and for BC. First, let us calculate for BA. For that, from the joint B, we have to look at the point A. In the point A, we are having a fixed support. If the fair end is fixed, the formula is 4EA by L. The length of AB is equal to 4 meter. The moment of inertia is 3I. So instead of I, we have to apply 3I. Finally, we are getting the stiffness for BA is equal to 3EI. Now, let us calculate for BC. For that, from the joint B, we have to look at the point C. The point C is continuous because after the point C, we are having a span CD. If the parent is continuous, the formula is 4EA by L. The length of BC is equal to 4 meter. The moment of inertia is equal to 2I. Finally, we are getting the stiffness for BC is equal to 2EI. Now, let us calculate the stiffness values in the joint C. From the joint C, we have to calculate two stiffness values for CB and for CD. First, let us calculate for CB. For that, from the joint C, we have to look at the point B. The point B is continuous because after the point C, we are having a span AB. If the parent is continuous, the formula is 4EA by L. The length of BC is equal to 4 meter and the moment of inertia is equal to 2I. We can apply. Finally, we are getting the stiffness for CB is equal to 2EI. Now let us calculate for CD. For that, from the joint C, we have to look at the point D. In the point D, we are having a hinged support. If the parent is hinged, the formula is 3EI by L. The length of CD is equal to 5 meter. The moment of inertia is 2I. We can apply. Finally, we are getting the stiffness for CD is equal to 1.2 EI. We cannot consider the point D as continuous because after the point D, we are only having overhanging span. In this case, we cannot consider the point D as continuous. Now, let us calculate summation of K. In the joint B, we have calculated two stiffness values. We can add both of them. After adding, we are getting 5 EI. In the joint C also we have calculated two stiffness values. We can add both of them. After adding we are getting 3.2 EI. Now let us calculate the distribution factor. The formula for distribution factor is K by summation of K. We have already calculated the K values and the summation of K. We can apply the values inside the formula and calculate the distribution factors. Finally, we are getting the distribution factors. For BA, it is 0.6. For BC, it is 0.4. For CB, it is 0.625. For CD, it is 0.375. Now, let us start making the moment distribution table. In the table, first let us enter all of the members. Then let us enter the distribution factor values. Then let us enter the fixed end moments. In the spans AB, BC and CD, we have calculated the fixed end moments. Let us enter them. For DE, we have already calculated the final moment MDE. Let us enter that also. We also calculated the final moment for DC, MDC, which is equal to minus 120 kilonewton meter. So we have to make DC 120. For DC, the fixed end moment is 100. When we add 20 with this 100, we will get 120. So we have released DC and we have to give the carryover from DC to CD. When we divide 20 by 2, we will get 10. Now let us find the adjusted fixed end moments. For AB, BA, BC and CB, there are no changes. For CD, we have to add these two values. After adding, we are getting minus 90. Now let us make the first distribution. We know that the distribution can be done only on the joints. Here there are three joints: joint B, joint C and joint D. In the joint D, we have DC and DE. For DC and DE, we have already calculated the final moments. So we should not make any distribution for the joint D. We have to only make the distribution in the joints B and C. Now let us do the distribution in the joint B. First, let us do for BA. For that, we have to add these two fixed end moments and then multiply with the distribution factor at BA. When we do that, we are getting a positive value. So we must enter inside the table as negative. Now let us do the distribution for BC. For that, we have to add these two values and then multiply with the distribution factor at BC. When we do that, here also we are getting a positive value. So we are entering inside the table as negative. Now let us do the distribution in the joint C. First, let us do for CB. For that, we have to add these two fixed end moments, then multiply with the distribution factor at CB. When we do that, we are getting a negative value. So we are entering inside the table as positive. Now let us do the distribution for CD. For that, we have to add these two values and then multiply with the distribution factor at CD. When we do that, here also we are getting a negative value. So we are entering inside the table as positive. Now let us make the first carryover. From BA, half of minus 24 will go to AB. So minus 24 by 2, we will get minus 12. We can apply that. For AB, the first distribution is 0. So we cannot make the carryover to BA. From BC, half of minus 16 will go to CB, and from CB, half of 43.75 will go to BC. We have to be very careful. We cannot make the carryover between CD and DC because we have already released DC and found the final moment. Now let us do the second distribution. Now in the joint B, for BA there is no value, for BC there is value. So we can make the distribution very easily because we have only one value. Let us make the distribution for BA. For that we have to multiply this value with the distribution factor at BA. When we do that, we are getting a positive value. So we are entering inside the table as negative. Now let us do the distribution for BC. For that we have to multiply this value with the distribution factor at BC. When we do that, here also we are getting a positive value. So we are entering inside the table as negative. Now let us do the second distribution in the joint C. For CB there is a value. For CD there is no value. So in the joint C also we can make the distribution very easily. Let us do the distribution for CB. For that we have to multiply this value with the distribution factor at CB. When we do that, we are getting a negative value. So we are entering inside the table as positive. Now let us do the distribution for CD. For that we have to multiply this value with the distribution factor at CD. When we do that, here also we are getting a negative value. So we are entering inside the table as positive. Now let us do the carryover. From BA, half of this value will go to AB. From BC, half of this value will go to CB. From CB, half of 5 will go to BC. In this way, we have to do more distribution and carryover until we are getting smaller values. I have done up to the 7th distribution, but it is not necessary. You can stop around 5th distribution or 6th distribution because we are getting smaller values like 0.094 and 0.062. But we should not forget when we make the last distribution, we have to give the carryover to the fixed supports. You can see that I have given the carryover from BA to AB because in the point A we are having a fixed support. That is why I have given the carryover to AB. No need to give the carryover to other members. Now we can add all of the values. We have to add the values from the adjusted fixed end moments. After adding, we are getting the final moments. In this analysis, we have calculated all of the moments. For MAB, we got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we got a negative value. So it is also acting in the anti-clockwise direction. For MBC, we got a positive value. That means it is acting in the clockwise direction. Previously, we assumed that MBA would be acting in the clockwise direction and MBC would be acting in the anti-clockwise direction, but our assumptions are wrong. For MCB, we got a positive value. That means it is acting in the clockwise direction. For MCD, we got a negative value. That means it is acting in the anti-clockwise direction. Now let us find the vertical reactions. First, let us take the span AB and calculate the vertical reactions. In the span AB, there are two moments. MAB, which is acting in the anti-clockwise direction, and MBA, which is also acting in the anti-clockwise direction. First, I am going to find out RA. For that, I am going to take movement about B. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 4 meter, so for RA. The point load 40 kN is acting towards the point B in the anti-clockwise direction, so it will be negative and the distance is 2 meter. Then we have two movements. Both of them are acting in the anti-clockwise direction, so both of them will be negative. Finally, we are getting RA by applying the rule sigma V is equal to 0. We can find out RB1. Now let us take the span BC and find out the vertical reactions. In the span BC, there are two movements, MBC, which is acting in the clockwise direction, and MCB, which is also acting in the clockwise direction. In this span, first I am going to find out RB2. For that, I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction. So it will be positive and the distance is 4 meter. So for RB2, the concentrated movement is acting in the clockwise direction. So it will be positive. Then we have two end movements, 19.6 and 58.8. Both of them are acting in the clockwise direction. So both of them are positive. Finally, we are getting RB2. For RB2, we will get a negative value. That means our assumption is wrong. We assumed that RB2 is acting upwards, but actually it is acting downwards. Now let us apply the rule sigma V is equal to 0 and find out RC1. Here we have to be very careful. When we apply the value of RB2, we must apply as negative value because it is acting downwards. Finally, we are getting RC1, which is equal to 39.6 kN. Now let us take the spans CD and the overhanging span DE together and find out the vertical reactions. When we take these spans together, no need to consider MDC and MDE because they will get eliminated. Only we have to consider MCD, which is acting in the anticlockwise direction. When we take moment about D, we can find out RC2. Then we can apply the rule sigma V is equal to 0 and find out RD. Now let us add RB1 and RB2 so that we will get RB. For RB, we will get a negative value. That means RB is acting downwards. Then let us add RC1 and RC2. After adding, we are getting RC. Now we are going to draw the shear force diagram. I am going to calculate the shear force values from the point A. In this case, I am moving towards right hand direction. Upwards will be positive and downwards will be negative. You can see the shear force values. Using the values, we can draw the shear force diagram. Now let us draw the free movement diagram. For drawing the free movement diagram, we have to consider every span as a separate simply supported beam and calculate the bending moments. First, let us take the span AB. In the span AB, there is a point load acting in the center. If in the simply supported beam, point load is acting on the center, The formula for calculating the maximum bending moment is WL upon 4. Using the formula, we are getting 40. In the span BC, there is a concentrated movement. The concentrated movement is acting in the center and it is acting in the clockwise direction. The formulas to find out the maximum bending moments are m upon 2 and m upon 2. Here the moment is 80, so 80 by 2 we will get 40. On the right of the moment it will be positive and on the left side it will be negative. Now let us take the span CD. In the span CD there is UDL 48 kN per meter acting for the full span. The formula to find out the maximum bending moment is WL square upon 8. After applying the values inside the formula, we are getting 150. For the point load and for the point movement, the free movement diagram will be in the shape of triangles. For the UDL, the free movement diagram will be in the shape of parabola. Now let us make the end movement diagram. In the direction of the movements, we have to make the diagram. If the end moment diagram comes above this line, that will be negative. If it goes below the line, that will be positive. So here and here it is negative and here it is positive. Now we can combine the free movement diagram and end moment diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.